Hello everyone and welcome to Sky Scholar. We now return to our analysis of the microwave background. For the time being, let us concentrate on the monopole, namely the blackbody spectrum, which we presented in the last video. I have often stated that in order to produce the blackbody spectrum associated with the microwave background, one must first have access to a vibrational lattice, as you can learn from this 2003 presentation. It takes more than a simple thermal equilibrium. A physical entity is required to generate the photons. Now, the vast majority of physicists will disagree with that statement. Most astronomers, for instance, believe that thermal equilibrium is enough, in large part because they have never thought about the problem. But if you follow this channel, you are familiar with the extensive series of videos that I've released relative to Kirchhoff's law and blackbody radiation. Most physicists cannot even state Kirchhoff's law properly. They often confuse Planck's law with Kirchhoff's, unable to see the tremendous distinction between the two. At times, they cite Stewart's law as Kirchhoff's law, not realizing that they are not the same. So before we go too far, let us make the subject clear. Stewart's law states that in thermal equilibrium, the emission of an object will be equal to its absorption. Of course, this is provided that no convection or conduction is operating. You can learn more about Stewart's law in this video. Unlike Kirchhoff's law, Stewart's law was derived from experiments. It is not simply deduced from theory. As for Kirchhoff's law, it extends much beyond Stewart's. It states that in the presence of temperature equilibrium, the radiation within any rigid opaque cavity will always be of the same nature. That radiation will be independent of the nature of the walls and depend only on temperature of observation and the frequency sampled. In other words, Kirchhoff advanced that blackbody radiation will be found in any rigid opaque cavity, provided that equilibrium is present. You can write Kirchhoff's law this way, wherein the emission observed from a small hole peering into a cavity is dependent only on temperature and frequency. Kirchhoff did not know the functional form of the radiation, but he advanced that it would be independent of the nature of the walls. At the same time, Kirchhoff's argument was entirely theoretical. He had no experimental proof for what he was advancing. On this basis alone, his paper should have been rejected, yet it eventually became a law of physics. But in science, laws stem from observation and experiment, not mathematics. Worse still, Kirchhoff's law has not stood the test of time, even in mathematical terms. There is no valid theoretical proof of Kirchhoff's law, and there never has been. You can learn more about this problem in this lecture and in this paper, where Planck's derivation of the law is shown to be invalid. Next, what about Planck's law? What Planck did was provide a mathematical form for the blackbody radiation curve. Planck's equation is clearly accurate and yields the correct answer. However, because Planck believed that Kirchhoff's law was correct, his work remains incomplete. Now, laws have consequences. It is because of Kirchhoff's law that astronomers and physicists believe that they can obtain a blackbody spectrum from the universe without the need for a physical lattice. Kirchhoff's law has enabled astronomers to argue that stars are gaseous plasma devoid of lattice structure, and that black holes will be able to produce Hawking radiation through pair production. In addition, because of Kirchhoff, Planck himself believed that blackbody radiation was completely independent of the nature of the walls, despite the fact that he always had recourse to a carbon particle in his text on the subject, as was reviewed in this paper. As a result of all this, Planck's equation is the only expression in physics which has never been linked to a physical cause, as I discussed here. It is true that the equation correctly gives a blackbody radiation formula. However, though Planck used oscillators in his derivation, he completely removed the need for a physical oscillator in accounting for the spectrum you see. If you believe in Kirchhoff's law, you do not require the oscillators. This has permitted astronomy to evolve without any need for physical reality, Blackbody spectra could be produced with a pencil using theory alone, provided that the scientific paper, at least at some point, invoked thermal equilibrium. Yet in order to obtain a blackbody spectrum in the laboratory, physics must have recourse to a nearly perfect absorber. Graphite and soot are often used. One would not build a blackbody from silver, and the reason is simple. You need a lattice that can both absorb and emit radiation in order to get a blackbody spectrum. The graphite and soot lattices meet this requirement, but silver does not, as polished silver is nearly perfectly reflecting in the infrared and the microwave. If you send any radiation into a graphite cavity, it will immediately be transformed into blackbody radiation, as we saw in these videos. But if you do so in a silver cavity, or in a modern extremely reflective cavity used in lasers, you will get standing waves if the incident radiation is phase coherent. The radiation will never become black, which is great, for otherwise lasers, MRI cavities, and cell phones would not work. As a point of interest for physicists, perfectly reflecting cavities can never achieve thermal equilibrium through radiative processes, precisely because they are unable to absorb the incident radiation. They reach thermal equilibrium either through conduction or convection. The radiation which they contain remains completely dissociated from their actual temperature. That radiation remains a function of the radiation which was incident upon the cavity. Perfectly reflecting cavities may or may not contain radiation, and that has absolutely nothing to do with their temperatures. The perfectly reflecting cavity can reach temperature equilibrium, but such cavities do not contain blackbody radiation unless that radiation was placed within it. As a result, Kirchhoff's law is false. Kirchhoff's law required temperature equilibrium, as you can learn through this English translation of Kirchhoff's work. The perfectly reflecting cavity easily meets this requirement. However, the radiation which it will contain will, in general, not be black. Of course, Kirchhoff was unable to study the perfect reflector using phase-coherent incident radiation. He lacked network analyzers and electronic test equipment. But if he had been able to study phase-coherent radiation and lasers, he would never have formulated a law stating that radiation contained within all opaque cavities must always be black and dependent only on temperature and frequency, while being independent of the nature of the walls at temperature equilibrium. So there is a lesson here, and the reason why I spent so much time on this channel treating Kirchhoff's law. Change in astrophysics is inherently linked to recognizing that Kirchhoff made an error. We need a distinct physical lattice to get a blackbody spectrum. An opaque enclosure is not enough, as our silver cavities with their standing waves prove. Of course, in 1862, Kirchhoff had no idea that silver cavities will someday be supporting standing waves. In any event, the lattice which seems to work best on Earth to produce a blackbody spectrum is the hexagonal planar lattice, which is found in graphite and soot. Such a lattice was never present in the Big Bang, and that is their problem. The Big Bang lacks a proper physical mechanism to produce the photons it claims. As such, this theory will not survive the passage of time and the careful re-examination of the requirements for obtaining a blackbody spectrum. Someday, someone will link Planck's equation to the physical world. The physical setting required to produce a thermal spectrum will be recognized, and that setting will be the vibrational lattice. So when the need for lattice structure becomes recognized, Big Bangs, black holes, and gaseous stars will no longer survive. That will be the first real explosion in physics, and it will take the form of cataclysmic change in physical theory. If you enjoyed the video today, promote the channel, mention the video to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on our next video.